Okay, so now we will be able to combine all the pieces of the puzzle to finally appreciate the quantum advantage to metrology. So again, we essentially start with the first protocol we saw, where we were using a quantum state as a probe, and I'll this time write it in terms of an interferometer. I started with the state on the Bloch sphere, uh, the zero state or the spin up state, and over here I have a quantum gate or a beam splitter or whatever, and I apply a, doesn't matter. The idea is that I apply a unitary operator and I rotate it by pi by 2 about the y-axis. So I get the plus x state. So again, making the Bloch sphere, I started from here. This was the state, and I rotated it to get the plus x state over here. And these are the two arms of my interferometer, or the beam splitter, you can say. I create an equal superposition of up and down, and in the arms of the interferometer, uh, I'm applying the Hamiltonian. So this can be an atom interferometer and these can be the magnetic fields, but essentially the idea is that I have an initial quantum state, I create an equal superposition of up and down. Now I'm going to apply it with the following Hamiltonian, where really omega is the kind of a parameter typically I'll be interested in. So what this does, it provides me a rotation, and each of the arms of the interferometer is going to pick up the phase depending upon the eigenvalue, as we've already discussed. So this is just a pictorial schematic of what we've already seen, and then again I'll make it go through a rotation. This was, remember, this was the Hamiltonian acts for this rotation, and again I'm going to flip it up somewhere here. This is going to be my final state. This was 4, this was 3 maybe. Yeah, so this was after the application of the Hamiltonian. This is my state 3, and this was what happens after I again rotated back to convert the amplitude information, sorry, the phase information into the amplitude information. This is exactly what we have so once I have converted this, the probability of detecting it in upspin is given by the Bond's rule, which was the probability of detecting it in the downspin. So these are going to be my series of measurements. Remember, M1, M2, Mn, and based upon these statistics, I'm going to infer the information about the phase omega. So what is my signal in this case, or what am I estimating? So let's say quantum mechanics tells me about the expectation value of z. Basically that means how many times the upspin occurred versus the downspin, and that you can calculate the way we calculate quantum expectation values is given by minus cosine omega t. That's just the expectation values I get from these statistics. With probability p up arrow, I'm going to detect the upspin, the probability of down arrow, I'm going to detect the downspin, and I can calculate the average, which comes out to be minus cos omega t. And the noise or the variance, remember the variance of the estimate, this quantity is the variance of the y estimate, which we already calculated uh, above, this particular guy over here. Uh, so that is going to be essentially 1 minus cosine square omega t, or in other words sine omega t. So as we discussed that, so this is in some sense my estimator, which has the information about the frequency omega embedded in it, and I repeat this experiment many times. I get the expectation value of the signal, which is my signal, and the variance, what is going to be the spread around the parameter, that is going to be given by sine omega t. Now, the narrower this process, or the narrower the variance, or the more clustered around the parameter I need to estimate the values, this is going to be given by the variance over here, and that's going to characterize my metrology protocol. So again, this is my estimator, which might have suffered from some sort of a bias, and of course I need to change the units. Remember, here I'm measuring sigma z as a signal, but in reality I'm more interested in measuring omega t, or some information about the frequency. So after converting that particular thing, taking into account the units, what do I get? I get the variance is essentially whatever my noise was, or the variance of the estimate, divided by our derivative factor, d signal over d omega t. Remember, this guy was taking care of the units into account. So what do I get over here? Let's say I do this experiment, this particular experiment. I'll just name it over here again. I take care of this protocol. I do this experiment many times for n independent atoms. So this entire scheme is carried out n independent times. So I'm going to repeat this guy n times, entire scheme n times. What do I get? My variance, or the quality of estimate, is just going to scale as 1 over root n, this thing. This is just from statistics. I repeat, the variance of any process or a random variables would go as 1 over square root of n, the number of times you repeat the protocol. So this is called as the short noise, or in some sense this is also called as the standard limit, standard metrological limit. So if you calculate this quantity, this entire thing, variance of sigma z over d signal by d omega t, what you get is, well, what you get out from here is just 1 over root n. So the scaling of my estimation of the parameter omega, the variance of the goes as 1 over square root of n. So if I have n independent trials or n independent atoms, and I am repeating this protocol for each atom, this is the scaling I get. So after each iteration, if I have to measure the frequency omega, I have to repeat it around 100 times to change the variance by square root of 1 over square root of n, or make the variance 10 times as short. 1 over, I'll just say 1 over square root of 100 times. So more times I repeat the experiment, the better estimate I'm going to get. This variance of this random variable is going to become narrower and narrower, but I'll have to repeat it many times. But essentially in metrology, what we are interested in is the scaling of these guys. So n independent trials of this experiment with n independent atoms give me a scaling of 1 over square root of n. Now the question now arises is, can we do better? Can we do better than a square root of 1 by n scaling? If you notice, so far we have not been able to exploit any quantum aspect. So far we have not been able to exploit any quantum property. Really, this 1 over square root of 1 scaling occurs for classical processes also. This is just the central limit theorem kind of an argument that the variance of a random variable scales as square root of 1 over n if I repeat this experiment n times. And you know, as you can guess, we introduced the entire machinery of entanglement, and we boasted that entanglement helps us perform quantum information processing tasks or quantum metrology tasks, which are superior than their classical counterparts. So we should be able to explore how, when the system I use n entangled atoms as compared to n separate iterations of the same experiment, how well I'm going to do. So let's explore that. So now using entangled atoms or quantum states, for interferometry or metrology. So over here I start with n atoms. I have n atoms and all of them are in a product state. You remember the Schmidt decomposition, just the number is 1. And now I apply a pi by 2 rotation to each of them. So what happens is that I create a superposition, and this is a very interesting superposition. It is n of them all having the upspin simultaneously, n of m having the downspin. So this was one of the examples we studied as an entangled state. Notice this state cannot be written as a product state. The Schmidt number is 2, and it's an equal superposition of all up and all down. This state popularly is also called as the Schrodinger's cat state. Either the cat is alive or the cat is dead. So now what do? I hit the state with my Hamiltonian, which was again the same guy, sigma z on all of them, tensored all of them. What do I get? I get each of the atoms is going to pick up a phase depending upon the orientation of its spin. So after I hit it with the Hamiltonian or the unitary e to the power of minus iota h bar t, and let me call it my cat state. This was my cat state. I get an equal superposition where the information I was supposed to have about omega that is embedded as the phase of the state. So this is after I've hit it with the Hamiltonian over here. And then finally, this state goes through another beam splitter or a rotation of each atom about the y-axis. And that gives me the entire information is converted from a phase information into an amplitude information. You already noticed that one interesting thing what has happened is that now the way we have set up this protocol using entanglement, using this Hamiltonian and simultaneously exploiting the superposition of all of them, each of this spins gives a contribution of minus omega t by 2 to the phase, and n of them give me n. So this n is a very crucial part which I have got. So in some sense, this state is rotating n times faster than my initial experiment with only one atom. So when the smoke clears, what do I do now? Now when I have that state, I'll just write down my state, the final, the fourth state as again over here. So again, I can calculate the probability. Now the phase information which was present in psi 3 about omega has been converted into amplitude information, and basically I can calculate the probability of all spins up as and P all down as shouldn't forget the important scaling part. Okay, so very interesting. You can already see that the fringe pattern I get has a period of 2 pi by n. So effectively, this measurement protocol is finer by a scaling factor of n, and that's very essential, and that's the whole point of this thing. We can do our statistics and estimation process. The expected value of the collective sigma z variable, that's going to be minus cosine n omega t. How well I am doing, I benchmark by the variance of this guy. That comes out to be n omega t, which comes out to be sine n omega t. And again, this was the variance of my estimator. I change the units, I convert, rescale everything. What do I need about it? So what do I get? I get something noise, which was nothing but my, I'll just write it down as the variance of this collective operator. So this is a collective operator, the variance of this guy divided by the change of units. which is my D signal. This just changes my units from an estimation of sigma z to an estimation of w. This was just a scaling factor I need to add. And what does it give me? It gives me a scaling of 1 over n. So this is kind of remarkable and fantastic that using, see, in experiment 1, what we did was we used n independent atoms. And the scaling we got was 1 over square root of n times, which was sort of a classical result, because any classical protocol through the central limit theorem would give you 1 over square root of n scaling. Through my quantum protocol, I used those n atoms, but I was able to combine those n atoms as an entangled state, an equal superposition of all up and all down, the Schrödinger's cat state of n atoms. And when I computed the variance of my estimates, rescaled it, I got 1 over n scaling. So this estimate is square root of n times more precise than my previous protocol where I used unentangled n independent trials. So this is called as the Heisenberg scaling, and this is arising because my initial quantum states were entangled, which is essentially a very quantum mechanical property. The Schmidt number here was 2. And this is one of the things in one avatar or the other is used in very sensitive metrology schemes, like, for example, detection of gravitational waves. When the ripples in time and space are happening and causing such minute effects, you need your instruments to be extremely precise, and you need a scaling which is as good as it gets. So quantum mechanics helps us achieve 1 over n scaling. Now, of course, the natural question that arises is, in quantum limited metrology, what's the best we can do? We already saw this was a classical scaling. Quantum mechanics helped us reach the Heisenberg scaling. So this was called as the short noise limit. Quantum mechanics helped us reach the Heisenberg scaling. Our estimation protocol became n times narrower using n entangled atoms. The question is, what is the ultimate bound? What can quantum mechanics do ultimately? Any aspect of quantum mechanics, you use the squeeze states, entangled states. So I must confess, I myself do not know the answer, but I know that there are schemes which help you achieve n3/2 of scaling. This uses, the implementations over here are using Bose-Einstein condensates, and very interesting quantum properties that helps us achieve this limit. Now again, the question is that, is this the ultimate? Who knows? Thank you.